you are aware, mass of neutron I can give this way, that is 1.0086 AMU. Mass of proton I can give 1.0078 AMU. Mass of electron, that is equal to approximately 1/1850 AMU. If these three masses are known, can I determine mass of hydrogen? Answer is yes. Number one, I can go this way, hydrogen H11. So neutron number 0, proton 1 and electron 1. So simply I have to add mass of electron plus mass of proton. Getting idea? But suppose I have to calculate mass of helium, which is 2,4. So what I have to do? 2 into mass of neutron plus 2 into mass of proton, because number of neutron is 2, number of proton is 2, plus 2 into mass of electron, that will give me mass of atom. So with this data, can I calculate mass of helium? Answer is yes. But there is another method that we can determine practically mass of atom. Now this is called as calculated mass, whereas on method we are going, that is called as actual mass. So we have now practically determination of mass that we are calling as actual mass, and we can calculate this way, that is called as calculated mass. Now there is general formula I have to prepare for calculated mass. This is simply, I can say Z into mass of proton. What is Z? You are aware, this is atomic number and mass number. Suppose X is element, I am writing here atomic number and here atomic mass number. So Z into mass of proton. So how many protons are there? Z plus Z into mass of electron, because how many electrons are there, that is also equal to atomic number. So that is also Z plus A minus Z. Why A minus Z? Because A minus Z is giving me number of neutron. So A minus Z into mass of neutron. So this is my calculated mass. So I am simply saying calculated mass, that is equal to Z into mass of proton plus Z into mass of electron plus A minus Z into mass of neutron. Now here Z is common, so I can take Z outside. What is inside? That is mass of proton plus mass of electron plus A minus Z into mass of neutron. Now what is mass of proton and mass of electron? You are aware, in case of hydrogen atom, there is one proton and one electron. So mass of one proton plus mass of one electron, that is equal to mass of one hydrogen atom, as previously we discussed. So can I substitute mass of proton and mass of electron as mass of hydrogen atom? Answer is yes, because hydrogen carries one proton and one electron. So I am replacing out here Z into mass of hydrogen. Many students are not able to follow this step. I am revising again, that single hydrogen atom is having one proton and one electron. So mass of one proton plus mass of one electron, I can consider mass of hydrogen atom. So in bracket I am writing here mass of proton plus mass of electron from here. So instead of one proton plus one electron, I can replace it by mass of hydrogen atom plus A minus Z, whatever the figure is there, into mass of neutron. So this way, by using this simple formula, we can calculate mass of any given atom. Now by using certain instruments, simple like mass spectrometer, like that equipments are there, we can calculate, we can determine, not calculate, we can determine practically mass of atom. This is called as, in this way I may say actual mass. Don't say americium. This is element, but here I am writing actual mass in order to make it easy. Now scientists, we are just analyzing data. Actually what is we are going to calculate mass, that must be same as actual mass. The theoretical mass and calculate observed mass should be same. This is theoretical mass, whereas this is observed mass. So theoretical mass and observed mass or calculated mass and actual mass should be same. But every time scientists observed that actual mass is found somewhat greater than calculated mass. Now actual mass should be equal to calculated mass because we are going by that same method, and so technically it should be same. But in case of science, many times we are getting this way that whatever you are expecting is not happening. We got always calculated mass is greater than actual mass. I am revising again. Calculated mass is always we got greater than actual mass. Can we check out for errors? Yes. There are instrumental errors, there are personal errors. We can nullify. Say same person is taking reading, then personal errors can be nullified. Then using same set of instrument, we can nullify instrumental errors also. But still, in none of the experiment we got this way that actual mass is greater than calculated mass. Always we are getting calculated mass is greater than actual mass. And therefore we have to accept the fact that calculated mass is always little bit greater than actual mass. I can't equate out this, carry out this by this way. So I have to make it equation. So in form of equation, I have to put here equality sign. That is equal to actual mass? No. A calculated mass is greater than actual mass. So I have to put here something figure that is we are calling delta M. That is called as mass defect. Suppose that figure is added, then only these two signs can be equated. So this is somewhat lesser than this. So whatever that lesser that we are adding here. In mathematical language, I may say as delta M tends to 0. The moment it is going to close to 0, then calculated mass will tend to actual mass. But this is not happening. Calculated mass is same as actual mass only in case of hydrogen atom. Why? Because it is having only single proton and single electron. So you can calculate or find out actually we are getting same mass, but rest of the time, that means for hydrogen delta M is equal to 0, therefore calculated mass is equal to actual mass. Put this value at 0, then we are getting Cm equal to M. Now here you are aware of now concept. Now delta M. Now this is in Greek letter, this is capital delta. Small delta we are showing something like this, whereas this is capital delta. So delta M is called as mass defect. Can I define mass defect? Let us check out. I have to find out what is mass defect. So I have to take this. So this I have to take on this side. So that is equal to calculated mass minus actual mass. So what we can going to define delta M? That delta M or mass defect is difference between calculated mass and actual mass. We found always calculated mass is greater than actual mass except hydrogen atom, and therefore the difference between calculated mass and actual mass we are calling that as mass defect. You are getting idea of mass defect. Now next question, where this mass goes? Why there is mass defect? Do you have any satisfactory answer for mass defect? Let us check out again. You are aware that great scientist Albert Einstein, he says that when mass is converted into energy, we can check out that with formula that E equal to m into c square. According to this formula, one can convert mass into energy. Mass that is in terms of, suppose I am giving in terms of kilogram, then c, that is velocity of light, should be in terms of meters per second square, meter per second. So meter per second bracket entire square because it is in terms of c square. You are aware that velocity of light is very, very high. So if little bit mass is converted into energy, it is converted into huge amount of energy. And that's why we are saying that if small amount of mass is lost or converted into energy, it is vast energy. Now here it's obvious for me that E equal to mc square. Scientists put out the value as delta m. This mass, where it is lost, this mass must be converted into energy. But for what purpose that energy is used? Energy is used to bind all nucleon together. And therefore they term this as binding energy. Don't say it is bond energy. This is binding energy. Bond energy is different concept which is there in chemical bonding, whereas binding energy is there in our nuclear part of chemistry or physics. So this is binding energy, that is equal to whatever the mass lost into c square. Now as I am explaining that we are not going to deep level, we are going to study only superficially, and therefore I must say simple, when 1 AMU mass is converted into energy, the energy evolved is 931. In some book it is given as 932, some book it is given as 932.5, 931.5, various figures are there. I am taking this as 931, and the unit we are calling as million electron volt. So actual unit is electron volt. We are putting prefix over here as million, that is 10 raised to, check out, 6. So this is also called as mega, because 10 raised to 6 is mega. So mega, but properly we are calling as million electron volt. So when 1 AMU mass is converted into energy, energy evolved is 931 MeV or million electron volt. Therefore, if delta m mass, delta m AMU mass is converted into energy, what is the amount of energy? What we are going to do, that energy is binding energy, that is equal to 931, say this is cross multiplication, this by this multiply by this, so 931 by 1 multiply by delta m, and so in short we can say that binding energy equal to 931 into delta m, and therefore we have formula that binding energy equal to delta m into 931 million electron volt. Now what is significance of this binding energy? Purely saying binding energy is not having that significance, because as value of A increases, you are aware that A means what? Atomic mass number. So as value of A increases, value of binding energy also increases. And so we are not able to conclude much of the things by binding energy. And then we have to consider a concept, that is average binding energy. Now this binding energy is there in nucleus, and therefore we are considering it only for nucleon. So what is average binding energy? So average binding energy, that is equal to total binding energy divided by number of nucleon. What is number of nucleon? That is A. You are aware what is nucleon? Proton plus neutron. So what is total number of nucleon? That is A. So this is called as average binding energy. Now here scientists are considering important figure again, that is comes to 8. Why? I don't know. But magically we are considering that average binding energy should be in range of 8 million electron volt. If atoms are having less than 8 million electron volt energy, average binding, then atom is unstable. Nucleus is rather unstable. And if binding energy per nucleon, or that is average binding energy, is 8 or greater than 8, then nucleus is extremely stable. initially till mass number 20, that means A equal to 20, binding energy, that average binding energy is less than 8. But number of particles are also less. Then onwards it comes to 8. Then it is at an, okay, this is simplified graph. Actual graph differs, but here I am drawing somewhat simplified graph. Here average binding energy we are putting here 8.5, 8. Then this line shows 8.5 million electron volt. Then I have to put graph here, that is something like this. So till 20 it is less than, for mass number 56 it is maximum, that is for iron. Then onwards it start decreasing out, and somewhere around mass number 140 it start decreasing out, and ultimately it goes below 8. As binding energy per nucleon is in range of 8, elements are showing high stability. As binding energy per nucleon decreases, it goes below 8, nucleus become unstable. Alright, so this is about nuclear stability we are discussing. In next part, we are going to discuss another aspects of nuclear stability, that is even and odd rule, magic numbers. All this we have to discuss in next part.